previous video, we discussed how we could use our knowledge of analytic geometry in order to evaluate very basic definite integrals graphically. And so what if we're going to try to evaluate integrals graphically, definite integrals graphically, for more advanced functions, right? Because in the previous video, we had perfect circular functions and linear functions, and so it was very easy to use our knowledge of analytic geometry. But here, it's a little bit more difficult, right? So if we have something as simple as f of x equals to x squared, and we're trying to kind of evaluate definite integrals of this function graphically, then it's a lot more difficult to use our knowledge of analytic geometry to obtain a very accurate solution, right? And so this is where we introduce the notion of Riemann sums. And essentially, what Riemann sums really is, it's a very crucial concept. Let me actually write out this guy's name. Riemann, I think it's with two N's. Okay, I don't know why my handwriting just decided to deteriorate. So Riemann sums, right? And essentially, this is a very, very important concept that's going to appear very much often in real analysis and more advanced mathematics courses. And this guy's name, Riemann, he's a very important German mathematician. His name is going to appear a lot as well throughout any advanced math course, so definitely get familiar with this notion. And the Riemann sums is kind of a very crucial concept. It's kind of the basis for a much more advanced topic, which is the Riemann integral, something that you will learn in real analysis if you take that course. And so essentially what Riemann sums is all about is essentially just dividing up or partitioning the x-axis into subintervals and then forming rectangles beneath the function in order to basically just sum up the area of all these rectangles to approximate a definite integral. And so let me tell you what I mean by that. Let me show you what I mean. Let's say we wanted to find the integral from 1 to 3, the definite integral from 1 to 3 of x squared dx. And we wanted to, use the Riemann sums method. So what we would do is we would go ahead and illustrate our interval on the real line over here. Let me make sure that this is accurate. That's not very accurate. Let's just say it looks okay. I know I'm struggling to draw a line right now. There we go. And so we have this interval over here, right? And this integral is basically just the area under the curve. It's this area right over here, bound beneath the curve and above the x-axis. And so what a Riemann sum is essentially just partitioning this x-axis into a bunch of very small rectangles. And so let me show you what I mean. Let's suppose we divide it up like this, right? We're just dividing this up. They don't necessarily have to be equal in base, but that's generally much more easier to do. It's much more conventional. And later on, when we learn how to actually write a Riemann sum as a limit, or an integral as a limit, then it will be a lot more useful to have equal subdivisions, so to partition the x-axis into equal parts. And so let's say we divide the x-axis into a bunch of parts, and then we were to take the, essentially take each of these subdivisions and form small rectangles out of them. So let's say we, go like this. If we just basically use the value of the function on the left to create the height of these rectangles, and again, we're going to learn that there are two different types of Riemann sums. There's a left Riemann sum and a right Riemann sum, depending on how we choose the height of our rectangles. Okay? And then essentially what we're going to do is we're just going to sum up all these areas, right? So we find this area right over here. We figure out this area, we call it A1. We figure out this area right over here, we get A2. And essentially we just keep summing them up until we reach AN, right? And that n is going to depend on how many subdivisions we have. If we have 100 subdivisions, then we'd have 100 different areas to sum up. And basically what we do is we just take the sum of all of these individual areas under the curve from these small rectangles, and that gives us a very good approximation of our definite integral. And so that method is the Riemann sums method. These individual little rectangles under the curve, those are the Riemann sums, right? And so essentially what this method is telling us is that if we can partition the x-axis into a bunch of small rectangles or a bunch of small little lengths, and then we use the value of the function to create the heights of these rectangles, and then we just sum up the areas of all of these individual small rectangles, then we will end up with a good approximation of our definite integral. And as a matter of fact, what we're going to come to find is that the smaller and smaller these rectangles are, so the finer the partition, the more accurate our Riemann sum approximation is. And let me show you. So let's say we used this Riemann sum over here, right? This one that I just drew out over here. If we were to use that as our approximation, let me just clear it up a little bit, then we would get a decently accurate approximation of our integral. But let's suppose that we went down here, right, let me draw this out again. And let's suppose we use slightly larger subdivisions. Let's say we did something like this. We chose something like this, right? We divided it up into 4 equal parts, right? They don't necessarily have to be equal, but again, just for convenience sake, we'll assume they are. And then we, again, went ahead and just used the value of the function on the left in order to create the heights for our rectangles over here, for our Riemann sums. Then you're going to come to find that if we sum up all these areas, there's a very big margin of error, right? There's a very big difference between the actual value of the definite integral and our approximation, right? Because here we're not accounting for this area, we aren't accounting for this area, neither are we accounting for this nor this. Meanwhile, if we go back over here, there's a very, very small margin of error, right? It's just very small little portions over here. So it's still not accurate, but it is much more precise than when we use larger subdivisions. And so essentially, this introduces kind of another concept for what a definite integral really is. It's essentially just dividing up the x-axis into a bunch of small rectangles. And this definite integral right over here is telling us that if we take all of these rectangles and we divide them up into an infinitely thin base, right? If we take the x-axis and partition it into infinitely thin lengths, then we will end up with the integral right over there, the accurate value of the area under the curve. So the way you can imagine it is that this little length down here, if we were to divide this entire x-axis, this entire interval of the x-axis into infinitely small pieces, we can call each of these lengths dx, right? Because dx can be thought of as a very small change in x. And so the smaller and smaller the change in x, or the smaller and smaller the base of the rectangle, the more accurate the Riemann sum approximation will be, right? And so as the kind of length of these rectangles become infinitely small, they approach this differential x over here, then the Riemann sum approximation becomes more accurate and we approach the actual value of this definite integral. So that's another way to kind of think about it, is that this integral right over here kind of tells us the sum of all areas, right? The infinite sum of all areas over the interval from 1 to 3. And the reason why we say x squared dx, why we take our function and then multiply by that differential, is because we're using the value of the function at each point to kind of be the height, right? So this tells us the height. Did I spell height right? Whatever. The height of each rectangle, while dx tells us the base, or the base length of each rectangle. So essentially, with that in mind, we can kind of interpret the integral, or the definite integral, as the sum of all infinitely small areas of rectangles, right? Within this sort of bounded interval from 1 to 3. And so that is kind of an approximation, or not an approximation, rather an interpretation of a definite integral, is kind of just summing up all of these infinitely small areas of Riemann sums. And so this is a very, very basic introduction to what a Riemann sum really is. It's essentially just partitioning the x-axis into infinitely small kind of rectangles, right? And partitioning the x-axis into infinitely small lengths, and then using the value of the function in order to have a height for each of these small lengths, a corresponding height to each length, and then summing up all of those areas, because those will form rectangles, and then we sum up the areas of all those rectangles to approximate what the actual value of the integral will be. And in the next video, we're going to look at particular types of Riemann sums.